Hi, welcome back. So we were doing trying to find solutions to the boundary layer equations, right, using a similarity variable, and we said we're going to divide these we're going to sort of categorize this set of problems. One is when the outer flow is non-zero, and when the outer flow is 0. So we kind of are done. We've also kind of touched upon a little bit as to how to use the energy equation, right? The last time we did this. So this is the energy equation, right? And now, so there is this theta. So theta is nothing but the non-dimensionalized temperature, right? So theta is basically it is nothing but the temperature minus the free stream temperature, right? Right. So temperature at the wall minus the free stream temperature. So that's basically theta that we're talking about, right? Right. So, so in the sense that usually we measure temperature, right, as a difference to a reference. Okay. So hence we are kind of taking this as a difference of the temperature from the free stream with respect to the temperature at the wall temperature as a difference from the free stream. So this is what theta is all about, and we got this equation 11, right? And you can see that we've got the Prandtl number and f dash and alpha 1, alpha 4, so on and so forth, and we've got the boundary conditions as well. Now this really sort of now calls for these. So this is the case that we kind of dealt with at the end, right? So the we've talked about wedge flow, corner flow, and things like that. Okay, so now let us just look at a little bit, for the case where the outer flow is 0, right? So what does that even sort of mean? So if I were to continue from here, right? So this is case 2 actually, right? This is case 2, which is the B part, okay? And that is that u zeta is equal to 0. That's basically the outer flow. Now it's actually kind of it's kind of a little unusual thing, right? I mean, how can you have a boundary layer even form if you don't have an outer flow, right? But something like at high Reynolds numbers, right? At very high Reynolds numbers, okay? Frictional layers or frictional layers, right, yield outer flows right. This is not to confuse that we don't have a fluid outside the boundary layer. It's just that the flow is at rest. Okay, so at very high Reynolds number, actually at a very high Reynolds number, what happens to the boundary layer? The boundary layer also has become very thin, right? So the frictional layers will yield outer flows at rest. So then in this case, if you have this is your say boundary layer, right? So this will basically cause your frictional, your viscosity is of course confined to this zone, right? This is your boundary layer. It is confined to this zone, but at very high Reynolds numbers, it can actually make this flow to go to rest. Okay, so hence Now, frictional layers, so I mean, to give you an example, right, they could arise due to, so examples say of say frictional layers. When can you see, frictional layers? Okay. Motion of the wall, right? So, for example, rotating disk. What is the best you can think of? Just think about it, okay? And another is a wall suddenly set into motion. Right? Or, something which is oscillating, or an oscillating wall. Right? So, you have brake discs, right, and there is a fluid which is attached, which is basically in between the discs. So, and if you have, if you could think about it, so if you have two, rotating discs like this, right, and due to the disc, if the fluid is in contact, with this disc, you will end up having, the outer flow, which is, velocity being 0. It is at rest. This is a possibility, okay? And a wall, of course, I mean, if you kind of just suddenly push it, motion is not suddenly, it's not going to set into motion, okay? And if, for example, if it sort of keeps going back and forth, then too, there is not enough, say, momentum generated to make a flow happen, right? That doesn't happen. So therefore, you do have outer flows at rest. Okay. So if how would I in such a case, how would I sort of use the similarity solutions, and solve our equations? So in here, so similar solutions are obtained. Okay, for now alpha 2 is equal to 0 here, right, since u is 0, right, and alpha 1 is 1. Okay, let's remind ourselves what alpha 1 and alpha 2 were. Okay, let me go and remind ourselves. There you go, right? If you see 6 here, right, if you see 6, so that's alpha 1, right, and you can see that we have d zeta of un, which this value is basically equal to the outside flow in this particular case, and that is un, which is u in this case, and this is 0, right. So since this is 0, so sorry, I mean, yeah, so this bit is, yeah, well, un, is that what we're talking about? Okay, we were talking about alpha 2, right? Where's alpha 2? So anyway, so this bit is this un, right? Un is the, yeah, well, we don't have the uz zeta here. This is the normal component of the velocity. So that's 1, we take that as 1, okay? u2 is this. Here, okay? u2 is here because this is equal to, let's see, what is alpha 2? Okay, there we go. So we've got alpha 2 here, right? Now that goes to 0 because the outer flow is 0, right? This itself is 0, right? So u infinity is 0, okay? And if I do that, yeah, so I guess I should just write this since I didn't. It's kind of causing a little bit of confusion, right? So this is what I mean is that when I say outer flow is 0, so basically we mean that the free stream is at rest, right? Outer flows. So therefore, this is 0 because this and alpha 1 is 1. So then again, equation 4, right, which is earlier derived, that becomes, so if you this is the equation 4 again written here if you see. So alpha 2 is 0 and alpha 1 is 1. So then what we get here is equation 4 then becomes f triple dash plus f of f double dash, okay, minus alpha 3 f dash square. Okay, this is so this is what we get. Okay, this is what we get, and now so therefore now what is interesting is that this is the type of solution I've shown you, right, using the little computer code, and so therefore just this can be solved very simply. Okay, now and in this equation, for example, if we take different values of alpha 3, right, you can solve it, you can get a solution, and each of that really results for a certain physical flow. So, for example, alpha 3 is equal to 0, right, so this term actually goes, right. So, what does the equation reduce to, do you think? So, this particular thing is, this is actually gone, right, that term. So, what we get now is basically this, right. So, this is something that we've already solved, that is the equation I showed you. So, what is this about? This is basically boundary layer at a moving plate, right. So, this is nothing but boundary layer at a moving plate, right. Okay. So, then alpha 3 is equal to minus 1, right. What we get is a free jet, okay, and alpha 3 is equal to minus 2 is wall jet, okay, and yeah, so, well, now for these two cases, actually, as this becomes very large, as basically the outside flow becomes very large, then yeah, I think that kind of makes sense, in the sense that the viscosity is kind of being undermined by the speed of the flow. Okay, in the sense that the momentum of the flow is kind of, or say, yes, the momentum of the flow is taking predominance over the viscosity. So that it's kind of intuitive. Okay, if something like this, right? So if you have a very thick fluid, right? So that's going to flow less, right? It's common sense that when it is very thick, it's going to be attached more to the surface on which it is moving. It's going to be very thick and resistant to moving, isn't it? If it is lighter, it will move. So now if I, however, force it with increasing its velocity, then it should be able to move. So it's like basically viscosity is nothing but it's applying a resistive force. So I apply, momentum to counter that, right? And therefore I mean that if the velocity is pretty large, right, for the same mass of the fluid, then I should be able to, counteract the resistive viscous forces. So that's what it means, but I think it's really intuitive if you think about it. Okay. Okay, so I think we've kind of covered it more or less. So the point is that if you just take the little computer code that we wrote, okay, and you solved it basically for this sort of an equation, right? The equation will have another term if you have alpha 3 is -1, -2, etc. If you're able to solve that, you should be getting solutions, and that should give you idea about free jet, wall jet, etc. Okay. Now, let us now look at this. I mean, we looked at the temperature, etc. We just took the equation, right? We took the equation, energy equation, and we were able to get something like 11. Right, this equation. So we got something like this, and your theta is nothing but the non-dimensionalized temperature, right. So now let us see if we can get some similarity solutions to the thermal boundary layer. Okay. So let's call this and say this is similarity solutions to the thermal boundary layer. Okay. Now, the temperature field is dependent on the velocity field. Well, yes, I guess. I mean, that's also, yeah, it's dependent on the velocity field. So we kind of, this is the energy equation that we looked at. Okay. So theta is of course the non-dimensional temperature difference. Okay. Now, let's just say the temperature field right, is dependent on the velocity field. Okay. Now, so therefore, if that is true, then for similar solutions to exist for the temperature, the same should exist for the velocity, right? So since we are there, so like we said, the dimensionless temperature difference, of course. Okay, so let me complete this. Therefore, for similar solutions, okay, I'm going to do that. To exist for temperature, okay, similar solutions should exist for velocity as well. Okay. Now, so therefore, so the dimensionless temperature difference, okay. So let us start like this. So dimensionless temperature difference. So that is theta is, this is a temperature difference, right? This. Okay, so now if I have that, right? Okay, let's just see. Yeah, so at, of course, this is the boundary condition, then at eta is equal to 0, of course, it's equal to the wall. Okay, and it's at the wall. Okay, so that now theta eta, right, is equal to 1. So then is equal to 1, then, well, then basically if that is true, right, if that is 1, so basically I am using this expression here. So zeta to the power n is equal to tw x minus this, right. Okay, so therefore, or okay, delta Tr is equal to Twx minus T infinity by zeta to the power n. So I bring basically this zeta on the right hand side at the denominator, right. Now zeta is something that we know, right. Zeta is nothing but x by L. So, or again, right, or delta Tr is Twx minus that x by L to the power n, right. Now let x be equal to L, right. So if L is, so x is equal to L, right, then delta Tr from just the expression up here, so the bottom basically becomes 1, right, is Tw L minus T infinity, right. So this is Tw, okay. So this is something we had written back up here, right. So I didn't explain that, okay, I didn't explain that too much. So this is what we had written. So T minus T infinity, Tw minus T infinity. So that's what we get actually, okay. So Tw, so how do we get that? So this delta Tr is nothing but this, okay. So Tw, okay. So you can keep the L, or it does not matter, it is basically at the wall, okay, minus T infinity. Okay. Now, there are, like we have been dealing with the Reynolds number, right. Reynolds number is something that we use when we define our flows. Now, the dimensionless characteristic number for heat transfer, you must be probably knowing this, is the Nusselt number. So, let us see what that is, right, and what we are going to do with it. Okay. So, dimensionless characteristic number right for heat transfer is the Nusselt number. Okay. So, Nusselt number, which is, so we will call that this. Okay. So the Nusselt number, again, that will depend on your x, is nothing but, right, okay, and alpha x is nothing but coefficient of heat transfer. Okay, so if that is there, so then how do we sort of write this a little more? Okay, so alpha x is nothing but coefficient of heat transfer. So therefore, I can write this. Okay, right. Okay. Right, this is the coefficient of heat transfer. Okay, so essentially this is the flux, isn't it? So then, if that is true, now this, right, this is what? This is nothing but right? This is basically at the wall, isn't it? So, so basically, lambda, lambda is the slope, right? Slope of this curve. So delta t, delta y, the way the temperature is changing along y. So that is essentially your lambda. The slope of that curve is basically your lambda. So which you can see from here. Okay. So this is, so it's similar to when we wrote down stress, viscous stress in the boundary layer. So okay. So then this I can I can write as minus lambda delta y, okay, T minus T infinity at the wall. Okay. If I do that, then I get this minus lambda del T del y at the wall, okay, plus lambda del T infinity del y. Okay, I'm sorry about this one, lambda, okay, and this thing at the wall. Well, clearly, of course, that's that doesn't change, isn't it? That doesn't change. So this is going to be 0. You understand why that's going to be 0, right? It's just the free stream, right? The free stream value doesn't change. Free stream value is a constant value. So at the wall, that doesn't change. So we get that 0. So therefore, Qx, right, at the wall is basically equal to, yeah, so minus right. And think about this. Why do we have a negative sign there? Think about that. Okay. So this is basically this Qx is giving you an idea as to how the temperature changes as you go away, as you go along y, right? As you go along y. So if this is your wall, and this is your y direction, right? So delta t, delta y gives you an idea about the wall, and you have a negative lambda, there, So how? So basically, what does the negative sign exactly mean? Think about that. Okay, think about that. I mean, that's a good question to sort of think about it. You can probably get the answer in a book, but I'd still like you to dwell on that a little bit and think about it. And use your common sense, take a little bit of, the way to do this is take, say, your tea cup, right, tea cup, put your hand at the bottom of the cup, right, and then, go up, don't burn yourself, but think about that, how the temperature is and things like that. Okay, that should give you an idea. Okay, so then this is equal to minus lambda del y t minus t infinity at the wall. Right? That's interesting, right? So we get that, okay? So, so we get, basically we get an expression for, Q W. So then we should be now be able to get an expression for, we'll go ahead and complete this, okay? So we are able to write it this way. So what happens to the Nusselt number, okay? So to the Nusselt number, therefore, right? So therefore, the Nusselt number, okay, becomes, right, lambda t w x minus t infinity. Now that is equal to, okay, L by lambda, just kind of writing it out, okay, dot, QW x. So I'm going to write that as minus lambda del t del y, right, at the wall, okay, or basically I can write this as, or this is equal to L by lambda t w minus t infinity, right, into minus lambda del y, which we are getting basically from here now, okay, t minus t infinity, right, at the wall, right. If we do that, so then this boils down to what? So therefore, this boils down to, okay, minus L. So basically the lambdas sort of cancel out. So I can say it is del y, okay, of t minus t infinity, right, t w x minus t infinity, okay, at the wall. Okay. So we'll kind of stop here, right. We'll continue this, okay, and look at the boundary conditions which we will use with this and what we arrive in the end. Okay. So I'll see you in the next module. Thanks for now.